Hello, I welcome you all in this presentation. This presentation is based on the weldability of the steels, and we will be talking about that what are the factors that matter for the weldability of the steels. So, weldability of steels. So, as I have talked in the last lecture, cleanliness of the weld, which is seen in terms of the maybe say inclusions and porosity, and this in turn is governed by the various factors like how effectively the cleaning of the base metal is done, fine surfaces of the base metal is done, the what kind of the groove geometry is used, groove geometry which may be U, V or J or single V, single U, double J or square like this. Then it is also affected by the kind of protection approach being used in welding, in a given welding process, and in addition to this it is also affected by the solidification conditions, and the base metal itself, sometimes the base metal contains the dissolved gases or the impurities in form of the inclusions. So, these directly contribute towards the presence of the gases and inclusions in the weld metal. Solidification conditions like the net heat input and the initial plate temperature, protection being used in a given welding process, like the process is like it is a CO2 vacuum or simple SMAW kind of shielding is used, SAW kind of shielding is used. So, depending upon the shielding approach being used for the shielding purpose, like the molten flux like in SAW, inactive gases like in SMAW, or the vacuum or inert gases. So, accordingly we will getting the different kind of the dissolved gases in the weld metal. We know that vacuum will be resulting the best results, thereafter inert gases, thereafter inactive gases, and the molten flux will be producing the different amount of the gases in the weld metal, and this is what also we can see from this typical diagram where nitrogen content in x axis and oxygen content y axis. So, here the GTAW results in the minimum oxygen and minimum nitrogen, and then we will see the GMAW process results in somewhat greater oxygen and greater amount of the nitrogen. SAW causes further larger amount of the oxygen and nitrogen, and then we will see the SMAW process. So, SAW, GMAW, GTAW and like say self shielded like FCAW processes. So, these since the protection approach being used is different in different processes, so they result in the different content of the oxygen and nitrogen in the weld metal. The groove geometry, the UVJ. So, the V groove geometry allows sufficient opening for the gases to come out as compared to the V and the J kind of the geometries. Then we have the cleanliness of the weld. If the weld is base metal is not cleaned properly, cleanliness of the base metal is important, like if the oil, grease, paint etc. is left on the base metal surface, so under the influence of the heat, these will be getting evaporated and get mixed up with the base metal, weld metal, and produce the inclusions and the porosity in the weld metal. So, cleanliness of the weld metal is affected by number of such factors which are related with the welding procedure, and these need to be taken care of. As far as the solidification aspect is concerned, like if the weld metal is solidifying slowly, then all the gases will be expelled, tendency for entrapment of the inclusions and gases in the weld metal will be limited. But if the solidification is fast, then all these gases and inclusions will have greater tendency to get entrapped in the weld metal, and thereby the presence, the cleanliness of the weld metal will be reduced. So, the solidification is governed by the H net and the T naught, apart from thermal properties of the material. So, greater the heat input, longer will be the heat, longer will be the time to for the transfer of the heat. So, solidification time will be long, solidification rate will be low, because it experiences with the high heat input, the cooling rate experiences is less. So, it takes longer time for solidification, and this will allow the sufficient time for these inclusions and gases to come out of the weld metal, and thereby cleanliness will improve. The similar kind of effect is also offered by the initial plate temperature. If the initial plate temperature is high, then cooling rate will be low, and longer solidification time due to the low cooling rate will be resulting in the cleaner weld as compared to those cases where the solidification rate is high. So, solidification rate in general affects the kind of entrapment tendency and the inclusion entrapment tendency. Then another is the hardenability of the steel. This significantly affects the ease of welding of the steel. So, hardenability of the steel is affected primarily by the composition. So, in general, higher the hardenability, lower the weldability of the steel. So, why this is so? Hardenability is also is about the ease of hardening. So, like say steel is hardenable if of say high hardenability, then after austenitizing, when it is cooled, it forms easily the martensitic structure and hardening of the steel. So, ease of hardening, if is high, ease of hardening is high, then it will result the hardening of steel easily through the transformation of austenite into the martensite easily, and this will result in the high hardness, reduced toughness, reduced ductility, and all these tendency and increased hardness, all these tendency, all these properties actually increase the cracking tendency of the steel welds. And if the weld is made with the cracks, then it is of no use. So, it requires more preheat. So, more efforts are required for preheating purpose. It will be more difficult to weld the preheated base plate as compared to the plate in the normal ambient conditions, and that is why we will see that as the hardenability increases, the cracking tendency of the weld also increases, and therefore, we require more care to avoid the cracking of the weld, and which in turn reduces the ease of welding or the weldability. So, the factors that affect the hardenability of the steel, one of the main factors that affect the hardenability of the steel is the composition. So, for that purpose, steel composition. So, what are the factors related to the steel compositions or the normal steel? Say, as I have said, in typical carbon steel will primarily be having the carbon, manganese, silicon, sulfur and phosphorus, where all these are the residual elements. Apart from this, the main element, the matrix is of the iron, while in case of the alloy steels, apart from the carbon, other alloying elements are also controlled like chromium, molybdenum, vanadium, aluminum, nickel, tungsten, etc. All these are added intentionally for realizing the specific set of the properties like the good toughness at low temperature or good resistance at high temperature. So, higher yield strength at elevated temperature or greater resistance to the softening at a higher temperature, etc. So, there can be various kinds of the requirements for which a specific set of the alloying elements are added, and each alloying element offers a unique kind of the effect as far as the welding is concerned. So, in which way these these alloying elements will be affecting the hardenability. So, we will see that to see actually the hardenability concept, we need to see the triple T diagram and CCT diagram, and for that purpose those diagrams will be seeing slightly later. First of all, we will see that from the composition point of view how the hardenability is affected. So, since there are various alloying elements in the steels, so effect of all alloying elements on the hardenability of a steel is checked using the one common term which is called carbon equivalent. Carbon equivalent is one parameter which is obtained by considering the relative effect of all alloying elements present in the steel which are having the effect similar to that of the carbon. So, the most common equation which is used for the low carbon steels and alloy steels is like this. So, CE basically one parameter which considers the effect of all alloying elements on the hardenability, and so this CE basically is related with the hardenability, and CE reflects that in which way different alloying elements will be behaving like carbon. That is why it is called carbon equivalent. So, here carbon is added as it is, then manganese divided by 6 plus chromium, molybdenum, vanadium divided by 5, nickel plus copper divided by 15. So, this is one typical equation which is commonly used. So, all these alloying elements are kept like this. So, here like the weight percentage present in steel is used to determine weight percentage of each of these elements present in the steel is used to calculate the carbon equivalent. So, this is one typical equation. So, another equation which is used for the micro alloyed steel to determine the carbon equivalent goes in like this, where in CE is equal to C plus silicon divided by 25 plus manganese chromium divided by 16 and nickel, molybdenum, copper divided by 20 and then vanadium divided by 15. So, this is another equation, and there likewise there are other equations also which are used, like there is another equation for calculating the carbon equivalent that goes in like this, where in CE is equal to C plus silicon divided by 30 plus manganese, copper, chromium divided by 20, nickel divided by 60, molybdenum divided by 15 and vanadium divided by 10 plus boron multiplied by 5. So, here weight percentage of each of the alloying element in the steel is put in these equations to calculate the carbon equivalent, and the carbon equivalent the calculated based on the composition is related with the ease of welding, since the carbon equivalent directly affects the hardenability, and the hardenability of the steel determines the cracking tendency of the steels, which in turn governs the kind of efforts required for avoiding the cracking in terms of the preheating or Krieger during the welding. So, the carbon equivalent is related with the ease of welding, and which we can see from the thing like if the Ce carbon equivalent is less than 0.45, then no preheat is used, and if the carbon equivalent is between 0.45 to 0.7, then preheat of 200 to 500 degree centigrade is used as per the carbon equivalent, and if the carbon equivalent is greater than 0.7, then the steel is found to be not weldable because it will impose a lot of cracking issues and the joint will not be good. So, the difficult to weld or not weldable above point C. In addition to this, the cracking tendency, which is due to the development of the hard, brittle, low toughness, low ductility HZ. Since the hardenability leads to these things, so and this happens primarily due to the kind of the cooling rate experienced by the by the metal, especially in the heat affected zone. For example, like this, the weld is made. So, if the heat affected zone experiences the low cooling, slow cooling rate, very slow cooling, then the hard, brittle, low ductility and low toughness HZ is not formed. So, to facilitate this, especially preheating is done, but the cooling rate being experienced by the heat affected zone is affected by the thickness of the plate also, by the thickness of the plate. So, thickness, if the plate is very thin, the cooling rate will be low, and in that case hard, brittle and the low ductility HZ may not form. So, that may not have the cracking tendency otherwise. That is why the carbon equivalent, in addition to the carbon equivalent, sometimes the thickness of the plate is also considered for determining the possible hardenability or the cracking tendency. So, for that purpose, instead of using just a carbon equivalent term, one additional term like compensated carbon equivalent is calculated. So, this is written as CCE, compensated carbon equivalent, which considers the normal carbon equivalent as it is, plus the thickness of parameter is also considered 0.00425 T. So, this is an empirical equations only to which considers the thickness of the plate. So, Ce stands for simple carbon equivalent and T is the thickness of the plate, in mm. So, obviously for even for the given carbon even for the steel of the given composition, if the thickness of the plate increases, then it will be increasing the compensated carbon equivalent, and for the compensated carbon equivalent the different kind of the scheme or the broad guidelines are used as far as preheat is concerned. So, for the CCE less than 0.4, no preheat is used, and the preheat for CCE in range of 0.4 to 0.7, the preheat of preheat from 200 to 500 degree centigrade is used, and CCE greater than 0.7 steel is not weldable. This is how in general we can relate with the weldability of the steels, or the kind of precautions that we need to relate the carbon equivalent or the composite carbon equivalent with the ease of welding or the weldability of the steels. Now, we will see that now sequentially we can go through to understand in which way the steel composition can affect the ease of welding. So, for this we need to see certain diagrams like iron carbon diagram and triple T diagram and CCT diagrams. I will try to summarize all these in one of using this approach, where like say this is a given steel, for example 0.3% carbon steel, okay, or we may consider like 0.8% carbon steel, anything. So, when the steel is welded, so this portion will be reaching to the molten state and the areas close to the weld will be reaching to the different temperatures like say 1200 degree centigrade, 800 degree centigrade, etc. And we know that different points will be experiencing the different weld thermal cycle like this. So, for point 1 and for point 2, it's the weld thermal cycles are like this, point 1 and point 2. So, the point 1 will be experiencing the greater temperature for longer duration as compared to the point 2. Point 2 will be experiencing lower temperature as compared to the point 1. Now, what kind of changes will be taking place at the point 1 and what kind of changes will be taking place at point 2 during the heating and during the cooling, that is what we will try to understand from this iron carbon diagram. You know, like say this is 0.8% carbon like this, and here like say 0, and this is the temperature. So, here like this is 910, this is 730 degree centigrade, and say 0.3% carbon steel is somewhere here. So, this is the gamma loop, here we have 1390 degree centigrade like this. So, here we have the gamma loop like this. This is corresponding to the 2% of the carbon steel like this. So, this is our the gamma zone, this is alpha plus gamma, this is alpha plus Fe3C zone. This is eutectoid point, right. So, here we will have just the perlite and this is the uniform zone. So, when the point 3 is heated, obviously the point 3 is heated say up to the 1200 degree centigrade. So, the point 3 will be experiencing the changes like this. So, here the point 3 will be subjected to the austenitic state, and since the cooling rates are quite high as compared to the point 2. So, while the point 2 will be heated, the point 2 will be heated for same point 3. So, this is for point 1 and point 2 will be heated to 2 phase zone, like say this is the maximum temperature for point 2. So, point 1 is being heated for much higher temperature for longer period, while point 2 is being heated just up to 800 degree centigrade for shorter period. So, how does it matter? For this we need to see this diagram, which shows in like how the time is affected as a function of temperature for homogenization. So, here in y axis we have temperature and in x axis we have time. So, how does it happen? Like say first of all our perlite transforms into the austenite. Here say what we have, perlite, ferrite, Fe3C and then carbides if they are there in the steel. So, as per the composition, steel and alloy steel in the room temperature conditions will have perlite, ferrite or cementite and then carbides if they are there. So, first of all perlite transforms into the austenite. So, here we have perlite on all these phases in this area, and as the heating continues at a high temperature, then what we get, our perlite transforms into the austenite. So, we get austenite plus ferrite plus carbides, all these things. For if heating continues for high temperature for long, then ferrite transforms into the austenite. So, we have austenite plus carbides. If further heating continues for long, then what we will have? Only the austenite, but this is inhomogeneous. Wherever carbon content is high, that will have the higher concentration of the carbon as compared to the other areas. So, this is inhomogeneous austenite, and if the heating continues for further long, then we will be having the homogeneous austenite. So, if you see this diagram, to have the homogeneous austenite, it takes long, and if it is just the plain carbon is steel, then this much time it will take, because in this case we will not have the carbides. So, so it takes long. If the temperature is high, it takes short, if shorter period to have the homogeneous austenite, and if the temperature is low, then it takes long. This is what I am trying to tell. The point 1 experiences higher temperature, it requires the shorter period to have the homogeneous austenite, and once we have homogeneous austenite, then only it will offer the desired structural transformations as per the cooling rate being experienced. So, the point 1 will be experiencing the higher cooling rate as compared to the point 2. So, the what matters here is that the temperature up to which any particular point in the heat affected zone is heated, that is important, and then how long it is kept under those temperature conditions, that also matters. It is the homogeneous austenite formation which is important for its transformation into the various phases as per the continuous cooling diagram. So, if we consider the continuous cooling diagram for this phase, then what we will have? We will have this one like this. So, in case of the continuous cooling diagram, this is say time, this is temperature, and this is time. Here this is the nose. So, our austenite, which is homogeneous at a high temperature, as per the cooling rate, here it transforms in this zone. So, what are these zones? This is homogeneous austenite region. Here we will have MS and MF zone, martensite start and martensite finish temperatures. So, here as per the cooling rate, say cooling rate 1 or cooling rate A. Cooling rate A is slow. So, here austenite first transforms into the proeutectoid ferrite. So, here we will have austenite plus ferrite, and then remaining ferrite will be remaining austenite will be transforming into the perlite, ferrite plus perlite. So, here basically we will have ferrite plus perlite, which is very fine. If the cooling this is very coarse, because cooling rate is very slow. If we use higher cooling rate like this, so here also austenite plus ferrite, here ferrite plus perlite, and then here transformation will complete, transformation of austenite into the perlite will complete, and here we will have fine ferrite plus perlite, fine ferrite plus perlite in this area. If the cooling rate is really fast, then we will have a whole transformation of all austenite into the martensite, and we will get the complete martensitic transformation. So, as per the cooling rate, if the point 1 is very close to the fusion boundary, it will be experiencing the higher cooling rate. So, it may change, it will be the homogeneous austenite, under the higher cooling rate conditions, austenite may transform into the martensite. So, the martensitic transformation will be brittle, and it will be leading to the high hardness. On the other hand, the point 2 is away from the fusion boundary, it experiences the lower cooling rate. So, lower cooling rate, as per the cooling rate, it may have the fine ferrite or perlite, or it may have coarse ferrite and perlite. So, in this diagram, if we see here, this will be the trend of increasing hardness. Initially we get the soft, like say 10 HRC, 20 HRC, and after the hardening we may have like say 40 HRC. So, as the cooling rate increases, our hardness keeps on increasing, and this happens due to the structural transformation from the austenite to the ferrite, and at the same time the refinement or the grain size is also affected. So, this is how we can relate the weld thermal cycle being experienced by the heat affected zone, and the iron carbon diagram, how the austenitic transformation take place, and then when the two different points cool at different rates, what we get at the room temperature subsequently on cooling. So, here the high cooling rate results in the martensitic transformation, which makes the heat affected zone very brittle and of the low toughness, while the point 2, which is away from the fusion boundary, experiencing the lower cooling rate, lower peak temperature, that will be having either ferrite, fine ferrite and pearlite, or it will have the coarse ferrite and pearlite, and so accordingly it will have its effect on the properties of the heat affected zone. So, now here I will summarize this presentation. In this presentation I have talked about how the different alloying elements affect the ease of the welding or the weldability of steel, and how the carbon equivalent can be related with the weldability, and in which way the properties of the heat affected zone can be related or can be understood using the iron carbon diagram and continuous cooling diagram. Thank you for your attention.